Thank you. Hello and welcome. I'm super excited to be here. In recent years, Pandas on Spark has grown out of bounds. Today, we will dive into this exciting topic and see how Pandas on Spark can help scale data science. I'm Xinrong. I'm an Apache Spark PMC member and committer with expertise on PySpark. I'm a key contributor of Pandas on Spark, and I work at Databricks as a software engineer. I came from San Francisco. I dance and surf. Shortly about Databricks, we are the data and AI company. We are the inventor and pioneer of the data lakehouse. And we are the creator of several successful open source projects. You can name Delta Lake, Apache Spark, and MLflow. And we are hiring. Here is the agenda of our session. First, we will see an introduction of Pandas, Spark, and Pandas on Spark. And then we will dive into the internals of Pandas on Spark, with a focus on internal frame and catalyst optimizer. Third, we will explore the scalability of Pandas on Spark. Lastly, we will see how Pandas on Spark goes beyond Pandas by utilizing the unified analytics in Spark. Let's start from the basics. So what is Pandas API? Pandas is the go-to tool for data manipulation and analysis in Python. It's deeply integrated into Python data science ecosystem. It's designed for single-node operations. So how do I scale? When faced with scaling challenges, there are several approaches to consider. First, upsizing. That is to allocate more resources by utilizing a large machine. However, that can be costly, and we may finally hit a ceiling in terms of scalability. Second, downsampling. We can choose a smaller and more representative data set for a quick result. However, that may lose granularity and potential insights. Lastly, by adopting a distributed framework, that is to harness multiple machines. Considering the limitations of upsizing and downsampling, a distributed framework is obviously the most robust and scalable solution. Apache Spark is a distributed framework. It's the de facto engine for large-scale unified analytics. It's seamlessly integrated into various ecosystems, which includes data science and ML, SQL analytics and BI, and finally storage and infra. It works both on a single node and a cluster. And PySpark is the Python API for Apache Spark. That's great. Spark helps scale. However, its syntax is different from Pandas, posing a learning curve for those who are already familiar with Pandas. So here's an example. The upper code shows how we can read a Parquet file into a Pandas frame and apply a filtering against the Pandas frame. And the lower code is how we can achieve the same functionality in PySpark. And we can see the syntax are totally different. With Pandas on Spark, we only have to change the imports, and then you are set to scale. Pandas on Spark implements Pandas API on top of Spark, very intuitive. And it brings the familiarity of Pandas API to the scalability of Apache Spark. It's first introduced as koalas in 2019, and is fully integrated into PySpark until 2021. We can import it as PySpark.pandas. And we have been improving the Pandas API coverage in Pandas on Spark. The figure shows the evolving coverage, which is categorized by main data structures, like data frame, series, and index. And for the most important data frame, we have reached 88% coverage. There's an ongoing effort to improving this number as well. We have seen what Pandas Spark and Pandas on Spark are. Now we will look at details of the internals of Pandas on Spark. So here is a simplified architecture of Pandas on Spark and Spark. Pandas API on Spark acts like a bridge to Spark SQL, which operates on top of Spark core. Spark SQL also has its own data frame API. In the next slides, we will see how a Pandas on Spark frame is different from a Spark SQL data frame, and how they interact with each other in terms of Pandas on Spark. When we call a data frame API in Spark SQL, it's like giving instructions. And Spark takes those instructions and creates smart plans, rely on Catalyst Optimizer. We will dive into this optimization process later. Here is a brief comparison between a Pandas on Spark frame and PySpark frame. Here, PySpark frame refers to the data frame API in Spark SQL. So their first difference is that a Pandas on Spark frame mimics a Pandas frame implementing Pandas API, whereas a PySpark frame it's more like a table and implementing relational operations. Second, a Pandas on Spark frame has both rows and columns identifiers called indexes as per Pandas. A PySpark frame only has the column identifier. Third, a Pandas on Spark frame is mutable. However, a PySpark frame is immutable. But despite all those differences, both frames share the same execution engine. The one from Spark SQL includes the Catalyst Optimizer we mentioned earlier. Before we delve into the internal frame, I wanted to set the stage that in Pandas on Spark, a data frame, a series, and an index, they are all backed by a PySpark frame. We've already seen the differences between a Pandas on Spark frame and a PySpark frame. Now we will see how internal frame fills in the gap. So internal frame is like a bridge connecting both worlds, Pandas on Spark and PySpark, and it carries critical metadata for the conversion. For example, PySpark columns, names, and data types of index and data columns separately. And when we make an API call to a Pandas on Spark frame, the internal frame will be copied with new state and with all of the updated metadata. And optionally, a PySpark frame will be created on demand. So we've seen the frame side. Now we shift our focus to the Catalyst Optimizer. This is a pivotal element in Spark SQL, which helps optimize the query plans, and Pandas on Spark heavily relies on that. The key technique used in Catalyst Optimizer is to represent queries as trees and then applying optimization rules for a better performance. We will dive into several optimization rules later. So Catalyst optimizes the query plans through several stages. Analysis is to understand the plan, and we improve the plan in the logical optimization, and then transform the logical plan into an actionable physical plan in the physical planning stage. And finally, we will generate the code in the code generation stage. So let's start with an optimization rule in logical optimization stage. It's called column pruning. So column pruning ensures that only necessary columns are read for a query. There is an example. We should read it bottom up. So we have a table with 5 columns, and we apply a filter over column C. Then we do group by A and get the sum of column B per group. And we notice that only 3 columns are actively used, that is A, B, and C. So column pruning ensures that only these 3 columns are read. It inserts a projection between the filter, and that's how it optimizes the query plan. The second rule is predicate pushdown. That rule moves the filtering operations closer to the data source. So in this scenario, we read a table R from Parquet files, and the table has 2 columns, A and B. We do filtering against the columns. Then we get the sum of both columns. And the predicate pushdown will push the filtering closer to the data source. So that rule will evaluate the filtering against the metadata in the Parquet file. And the metadata involves the chunk details, which includes the maximum and minimum value of that chunk. In this way, that rule can help skip unnecessary data chunks, then optimize the general performance. That's the rules I wanted to share for logical optimization stage. Now let's move on to the physical planning stage. So in this stage, we actually transform the optimized logical plans into actionable, executable physical plans with the best strategies. Let's walk through an example together. Here we have a query. We have 2 tables, A and B. We do the join, and then apply filtering. Finally, we group by the A1 column. The output showcases the column A1, the unique A1 value, and the corresponding sum of B1 values. So the left-hand side in green is the optimized logical plan, which is optimized by the rules we just mentioned. And the planner transitions this logical plan to the physical plan on the right-hand side. And we notice that there are 2 hash aggregates. The one before the shuffle is the partial aggregation. The one after is the full aggregation. So full aggregation means that all the values of one key needs to be on the same machine in order to do the aggregation. And we noticed that Spark helps us choose the broadcast hash join strategies. There are multiple join strategies, and Spark evaluates the filtering on B and thinks the filtered data B is small enough. And with broadcast hash join, the filtered B will be broadcasted. In that case, we don't need to shuffle A. That reduces the cost and improves the overall performance. So that's all I wanted to share about the internals of Pandas on Spark. Now let's explore the scalability of Pandas on Spark. So using Pandas on Spark, we found it scales very well across large clusters of nodes. We conducted benchmarks against common statistical operations, such as standard deviation, median, and mean, and also the group by and join operations. The chart demonstrates the performance when analyzing 15 terabytes Parquet data with different sized clusters. And each node in the cluster has 8 CPUs and 61 gigabytes of memory. And each bar in the chart represents the execution time of an operation for a specific cluster size. A shorter bar indicates a faster execution time. From our analysis, we concluded that the distributed execution of Pandas API scales almost linearly in this test scenario. Specifically, when the number of machines doubles, the execution time halves. The speed up when compared to a single machine is also significant. For instance, in the standard deviation benchmark, a cluster of 256 machines can handle about 250 times more data than a single node in about the same duration. All nodes in this test have the same configuration as mentioned in the previous slide. As we mentioned before, Pandas is designed for Python data science via batch processing, whereas Spark is more for unified analytics. And here, unified, that means SQL, ML, and streaming. Pandas on Spark has provided multiple ways for advanced users to leverage unified analytics in Spark. So the graph shows how we can do convergence among frames in Pandas, Pandas on Spark, and PySpark. And for example, both Pandas on Spark frame and PySpark frame can be converted to Pandas frame via toPandas method. They can also be created out of a Pandas frame. And between Pandas on Spark and PySpark, we support the toSpark and Pandas API for the conversion. So those API enables users to leverage functionalities across all three. Pandas on Spark also support users to query data via SQL, which is backed by Spark SQL. In this example, we create a Pandas on Spark frame, and then utilize the ps.sql API, which takes in a SQL query to count the number of rows in this data frame. And since Pandas on Spark queries are evaluated lazily, so we can forecast the most costly operations before the actual execution. And in this scenario, we leverage the Spark.explain API. There's an example. We have two Pandas on Spark frames, and we want to do the drawing. By calling the explain API, we can see in its physical plan, we use the sort merge drawing as the drawing strategy. In the catalyst optimizer section, we mentioned that there is a better drawing strategy for joining with a small data frame. So let's assume we have one of the frame is very small. So we can use the Spark.hint API to mark the frame small enough for the broadcast hash join. And then we call the explain method. We can see that the physical plan is rewritten. And finally, I wanted to mention that Pandas on Spark frame work with ML flow models. In this example, let's assume that we already initialized ML flow, including its client, and we have set up our training data and trained a linear regression model, which takes in value x1 and x2 and predicts a value. And in this code, we just search the run, get the model, and create a Pandas on Spark frame. We can utilize that model retrieved and use that model to predict the value against the data frame, and that's our result. That's all I wanted to share today. I wanted to express my gratitude for all of your time and engagement. I hope this exploration on Pandas on Spark can provide some insights for you to bring to your daily data science endeavors. And now I think we can enter our QA session. Thank you.
Xinrong, thank you so much for your talk.
Thank you.
I have so many questions here, so I will start right away. Anonymous question is, how is the PySpark Pandas API implemented internally? Is it just wrappers, or did the developers needed to go deeper in the Python/C?
Let me make sure that I understand the question. So the question is like that, whether Pandas on Spark is a wrapper of PySpark API, or it goes deeper into the
Python/C. I think
Yeah.
there's a typo. Or Python, I don't know. I'm not a professional.
Yeah, so one quick answer is that the major implementation of Pandas on Spark lies in PySpark. As I mentioned about the internal frame, which connects a PySpark frame to a Pandas on Spark frame. So yes, it is a wrapper. When you call a Pandas API against the Pandas on Spark frame, it will go through the internal frame and finally modify and manipulate the PySpark frame. But we also have an optimization layer, not only inside the PySpark catalyst optimizer, but in between the PySpark and the Pandas on Spark, just to increase, enhance the performance of Pandas on Spark. But I think because of the typo, I'm not sure whether that answers the question.
Maybe whoever asked the question can find you later and clarify.
Yeah, sure,
Perfect.
sure.
Okay. Next question by Vojta. Where to start with Spark? So that we understand the difference between PySpark, Spark Pandas API, and pure Spark. Any recommended learning resources?
Yeah, that's a really good question. So, like, in order to learn Pandas, like, since Pandas is a very mature library, if you go to their website, there are tons of learning materials. And for Spark, yeah, we also, like, in the Apache Spark official website, it also have a lot of, like, onboarding guides on both PySpark and Pandas on Spark. But I think, like, a quick rule or a quick principle for the learning process is that for the API side, we can assume that Pandas on Spark and Pandas share the same API layer. So from the usage side, you only need to learn one set because we aim to reach parity with Pandas on Spark. And if you wanted to learn more about the optimizations and more advanced side, as I just mentioned, to utilize the unified analytics, yeah, you should like go deeper into the PySpark user guides in order to leverage the analytics functionalities. That's my answer.
Thank you. In Spark on Pandas, is Spark on Pandas more CPU or memory intensive typically? In the benchmark, example machines in the cluster had a ratio CPU memory of 9:61. So this is a performance question.
Can I see the question?
Of course. Is Spark on Pandas more CPU or memory intensive typically?
CPU or memory intensive typically. I think that really depends on like the exact use case and workloads. So when you ask more intensively, are we comparing Pandas on Spark with Pandas? So I think Pandas, the main reason why we have Pandas on Spark is that Pandas only works on single machines, so it doesn't scale. And Pandas on Spark actually solves that scale problem. So yeah, if you go into the link I shared on the benchmark slides, we also did a performance comparison for single node operations, like with large data. For some operations, we are faster than Pandas. And for the others, when Pandas reach the out-of-memory era, we can succeed because Pandas on Spark is lazy evaluated. It doesn't load everything into memory in each step. So like that's the first part of question. And the second part, in the benchmark example, machines in the cluster had a ratio CPU memory of 9:61. I don't think so. I don't think I have that ratio in my slide. So I'm not very sure about the second part of the question, but feel free to clarify with me after the QA session.